The product that our group has been tasked to find is for an appropriate material and design a suitable finishing process for optimal performance is for a bathroom safety handrail. This is similar to a grab rail in that it is used to withstand a certain force. The main functional purpose of the handrail in a bathroom setting would be to assist a person in maintaining balance, lessen fatigue while standing, and holding weight while moving in case of slip. For example, one application of this product would be for when a caregiver would use a handrail to transfer a patient from one place to another. Therefore, handrails must be designed to withstand a high load and sudden impacts and must accommodate for people with disabilities. The construction and design of a handrail must conform to building regulations which specify the load it must bear. They are generally mounted to masonry walls or dry walls by using a strong wooden stud. Handrails are typically made of stainless steel, plastic, aluminum, fiberglass, or galvanized tubing. Since the environment of the product is in a washroom and is exposed to wet areas, the handrail must be designed to be waterproof. Typical finishes to the product include slip resistance, as this is required to ensure that the handrail is easier to grip, powder coated, epoxy coated, and polished to provide it with more aesthetic finish. The diameter of the handrail is important as a very large diameter weight and small diameter may not be durable and will require a greater force for user to sustain a grip. Given that the use of the product is for washroom setting, a typical location for the handrail would be next to a toilet to help people using a wheelchair transfer to the toilet seat and help people that have difficulty sitting down with balance. Another location would be in a shower or bathtub as it would help maintain balance and maneuvering and assist disabled people in transferring into and out of the closure. The positioning of the actual handrail depends on the positioning and situation of the person of interest, as it can be designed to be horizontal, vertical, L-shaped, and it can be at an angle.
The initial research led us to the engineering specifications set by the Americans Disabilities Act, or the ADA. The ADA guidelines state that the grab bar must have a diameter of 32 to 38 millimeters, have a 38 millimeter clearance from the wall, have no rotation in the fittings, withstand 250 pounds of force, or 1,112 newtons, and be a minimum 36 inches long. For the MPI derivation, the following design requirements were used. For the functional requirements, it was to support a load of over 1,112 newtons and do not deflect over 0.01 meters. Geometric, have a length of 90 centimeters. Objective was to minimize the mass, and the free variables were the material properties and radius for the purpose of the MPI derivation. The mathematical expression for the objective was given as m equals pi r squared L rho. This gives the mass of the bar when we assume that it's a beam as a cylinder. For the two functional requirements, the following equations were found. The stress is equal to force over area, and the deflection is equal to the force times the length cubed over 48 times the Young's modulus times the second moment of inertia for a cylinder. Using these two equations, it was found that in the MPI, we must maximize both the yield strength over the density and the Young's modulus, the root of the Young's modulus over the density. For the initial MPI plot, we plotted the log of the yield stress equals the log of density plus the log of M1, where M1 is the maximum force times the length over the mass. And the second line we plotted was log of the Young's modulus equals 2 times the log of the density times 2 times the log of M2, where M2 consists of the length, the force, the deflection, and the mass. This gives us the initial plot. However, this did not narrow down the options to an acceptable amount, and thus we added additional stages of constraints to reduce the variety of materials. The first stage was to get rid of natural materials such as wood. This was because the bar would be subjected to high temperatures and humidity. This can cause rotting and weakening over time. It is also porous and thus harder to clean in an environment which would be needed to be sanitized often, such as a bathroom. The second stage was to add a requirement of resistance to corrosion from water and alkalis. Since this grab bar will be used in the shower, water and soap will come into the contact often. Even though coatings can prevent corrosion due to these factors, it is much safer to have a material naturally resistant in case of abrasions on the surface collecting over time. The last stage was further riddling materials that are unrealistic or unnecessary to be used in the setting. Glass was removed as it shatters brittly and dangerously. Even though the material passes the loading constraint, if something went wrong, the failure would be much more dangerous than ductile or even brittle failure from a metal. Graphite was removed as it is much too expensive for this purpose, and there's no reason to expend extensive amounts of money for a grab bar. We decided to add an extra stage removing all non-metal materials. This step is not necessary in real life for real grab bars. However, we must create a heat treatment process for the materials we chose in this project. Thus, within this course, we must choose a metal to process. All these stages cause the possible materials to be reduced from 3,985 to 543.
The AC201 stainless steel was chosen over galvanized due to the stainless steel price is slightly higher than the galvanized steel since it only requires a small size production. But the corrosion protection offered is superior since all the material is corrosion resistant rather than just the coating. Besides, stainless steel has a better looking visual presentation, which is another important aesthetic factor at the moment to buy a product. Another important factor when comparing a product is only to mention that the product is made of stainless steel tends to transmit more confidence to the average customer with respect to the overall quality of the product. AC201 is also the cheapest alloy stainless steel from our MPI derivation. From our MPI calculations, all these alloys fulfill the requirements because of the price. AC201 shown to be more adequate alloy. Whether they are referred to as a water closet, toilet, restroom, or bathroom, these facilities fundamentally exist to safely dispose of human waste and to prevent environmental contamination and the spread of disease. Any discussion about an application that significantly affects the health, safety, and welfare of humans and our environment is inevitably about sustainability. The materials need to be highly cleanable, long-lasting, and capable of withstanding scratches and other deliberate damage. Several factors can contribute to material deterioration in these environments. High humidity, corrosion, bleach-containing cleaning products, urine concentration, and for outdoor standalone units. Exposure to coastal or dicing salt or corrosive pollutants. Due to all of the above mentioned, the normal form of AC201 to be a corrected choice for the environment described above. A corrosion protection method would be unnecessary and would only increase the cost of production. Type 201 stainless steel cannot be hardened by heat treatment, but can be cold worked. AC201 is not hardened by heat treatment and is annealed at 850 to 1950 Fahrenheit, followed by water quenching or rapid air cooling. Knurling is a manufacturing process typically conducted on a metalworking lathe whereby a pattern of straight, angled, or cross line is rolled into the material. The operation is performed for producing indentations on a part of a workpiece. Knurling allows hands or fingers to get a better grip of the knurled object than would be provided by the original smooth metal surface. Diamond knurl type is used to provide better grip on components and is the most common type used on everyday objects. Applying a knurling process to our bathtub will increase significantly its grip.